Là, c'est juste que comme il y a une séance qui n'a pas porté dans ce contrat, en décembre, on n'a pas prolongé son contrat.
Ok.
Et qu'on a depuis novembre, alors on fait le boulot, on a chaque fin. Jusqu'à la fin de la semaine, au moins jusqu'à la fin de la semaine.
C'est votre chef, c'est qui?
C'est pas ça.
Ok. Côté RH, je sais pas.
Oui, enfin, la chef des assistants du chef de service.
Ok.
Après, côté RH, le service c'est moi.
Ok.
4 équipes, pas d'assistants.
Je peux faire un test de 3 heures.
Oui, il cherche à recruter. CG.
Ouais, attends. Tac. Attends, et quand je fais ça, ah, c'est cool. Je peux avoir toutes les slides là, sans que ça change ici. Tac.
Good morning, everyone. Thank you to the audience for being here. I'm very happy to present my thesis today.
Okay, are we ready? Hello, everybody. Welcome to the PhD defense of Mr. Erwan Normand. Erwan, welcome. Good luck. I'm Sinan Halio. I'm been selected by my peers as president of the jury. It's a great honor. Thank you very much. I will quickly introduce the members of the jury before we can start with the defense. I will start with online members. We've got from Korea Kyungkyu University, Professor Sokyu Hyun. We have online that you can see over there. And the other reporter is Jan Grubert from Coburg University on my right. Also online, we've got Martin Haché from Bordeaux. And this is the board of external members, and we've got also the thesis directors and supervisors, Claudio Paccaretti, Maud Marshall, and Eric Marshall. Erwan, it's your turn. You've got like 45 minutes to present your works.
Good morning, everyone. Thank you, Mr. President, for your introduction, and thank you to the jury for attending this defense, and thank you, everyone, for being here. I'm very happy to present my thesis today, which is about hand interaction in augmented reality with wearable haptics. Augmented reality, or AR, is a technology that integrates interactive virtual content into the real-world perception of a user. When implemented as a headset, as you can see on the video, it creates a portable experience that allows the user to freely navigate into the augmented world and to interact with it using their hands. Such an interaction can be done with virtual objects, but AR can also visually modify and augment real objects. However, hand interaction with virtual and augmented objects can be difficult and not realistic if it lacks compelling touch feedback. Our objective with this thesis is to improve hand interaction with virtual and augmented objects in AR using wearable haptics. Haptics is a study of touch and user interfaces that involve touch. Touch is a rich and complex sense. It is made up of different sensory receptors that are embedded into the skin and the muscle, and that are sensitive to many stimuli such as pressure, vibration, force, or temperature. These receptors, together with the dexterity of the hand, enable us to perform many interactions with objects and to perceive their properties such as texture, shape, or weight. In this thesis, we focus on the perception of augmented texture and the manipulation of virtual objects, as we will explain later. Due to the complexity of touch, there are many types of haptic devices. They can be divided into three main categories. Graspable devices are held in the hand, such as a robotic arm, as in the figure, or a game controller. Touchable devices are capable of dynamically changing their shape or surface properties, such as a variable friction surface. Finally, wearable devices are directly worn on the body and provide tactile sensation to the skin. Because they are small, lightweight, portable, and don't restrict user movement, they are particularly interesting for AR interaction. Here's an example where a user is capable of interacting with both real and virtual objects with wearable haptic feedback. And on this second video, we can see a wearable haptic device that folds and unfolds on the fingertip to provide on-demand contact with virtual objects. So in these two videos, the haptic is provided, feedback is provided to virtual objects, but it is also possible to create haptic augmented reality. With AR, we integrate virtual content into the real-world perception. It is possible to add virtuality to the point of masking the real-world perception, thus created virtual reality. And then AR and VR can be applied to all the senses, such as vision and touch. And we can thus have a different type of visuo-haptic augmentation. As we already mentioned, a real object can be augmented only visually, such as changing its color. A virtual object can be provided with virtual haptic feedback. But a real object can also be augmented with haptic feedback, such as changing its softness perception. Note that the real object here is not modified, only its perception when touched with the finger is altered using wearable haptic feedback. Such wearable haptic augmentation have been used in VR, for example, to simulate medical palpation. However, wearable haptic augmentation has not yet been integrated with AR headsets. In this context, we identified two research axes for our thesis objectives. In the first axis, we propose to design and evaluate the perception of visuo-haptic texture augmentation of real surface. This is important because visual augmentation and haptic augmentation can be perceived as incoherent with each other or with the real sensation of the surface. And we specifically focus on texture because it is an object property that is well perceived by both vision and touch, and because it has been well studied with wearable haptics. And with the second axis, we focus on hand manipulation of virtual objects. Grasping, moving, and rotating virtual objects are fundamental interaction in AR and VR, as they can be difficult to perform without haptic feedback. Additionally, current AR headsets have rendering issues that makes depth perception of virtual content difficult. That's why we propose to design and evaluate visuo-haptic augmentation of the hand as interaction feedback with virtual objects. We present 5 contributions in this thesis. For the first axis, we first design a system for rendering wearable visuo-haptic texture augmentation. We then evaluate the perception of haptic-only texture augmentation in AR versus VR. Finally, we investigate the perception of simultaneous visuo-haptic texture augmentation. And for the second axis, we first explore visual augmentation of the hand. Then we explore wearable haptic feedback for the hand in combination with visual hand augmentation. And we start with our first research axis, which is the visuo-haptic augmentation, the visuo-haptic texture augmentation of real surface. And we first present the design and rendering of our texture augmentation system. With a vibrotactile device, it is possible to simulate haptic texture. More precisely, it simulates roughness, which is the perception of the microgeometry of a real surface. It is, for example, the perception of fibers of wood or the asperities of brick. Roughness perception has been studied on real surface, in particular with grid texture, such as here, which is a parallel line that are equally spaced on the surface. And so, by placing a virtual vibrotactile device on the finger, it is possible to increase the roughness perception of the real surface by providing vibrations that are well synchronized with the finger movements. A common method to achieve this is to simulate such grid texture using a sinusoidal signal. And one particular thing with the signal is that the frequency of the signal is proportional to the finger speed. meaning that when touching the surface, it creates the illusion of touching a virtual grid texture with a fixed spatial period. Rendering such vibrotactile texture relies on estimating the finger speed in real time, and previous work has either used complex mechanical system to track the finger movement but constrain the movement of the user, or impose the fixed speed to the user. That's why, with those contributions, we propose a system that allows the user to freely touch and explore vibrotactile texture augmentation, but also to see this vibrotactile augmentation with any angle, thus creating the illusion of augmented surface. We now describe the system design. An interaction with a real object can be represented as a perception action loop, where touch sensations are perceived as feedback on action to the real object. There is also the proprioceptive feedback, which is the internal sense of the position and movement of the body. We then employed a vibrotactile device attached to the middle phalanx of the finger and a HoloLens 2 AR headset to display the visual-haptic texture to the user, which are combined and aligned with the real environment to create the illusion of augmented surfaces. Finally, to complete the AR perception action loop, we used camera and fiducial markers to track the real hand movements, reconstruct them using a virtual hand technique to simulate the interaction with the virtual environment in order to provide the feedback to the user. And now we focus on the rendering of the vibrotactile feedback. We start with the same vibrotactile feedback we just described, a sinusoid with a frequency proportional to the finger speed. Yet the cameras run at 60 Hz, while the vibrotactile voice call device requires a kilohertz signal. Then, when we estimate a new finger speed and update the signal frequency, it creates a discontinuity in the signal that negatively affects the roughness rendering and its perception. And we can solve this issue by adjusting the phase of the signal when updating its frequency in order to make it continuous. Finally, we chose a square wave signal to better simulate the sensation of crossing the edges of the grid texture, as we can see on the video. And we also use the position of the finger to delimitate rendering area where the virtual texture is displayed. And the virtual texture can only be felt when the finger is touching the real surface in order to create the illusion of an augmented surface. To conclude this first contribution, we proposed a system for rendering visual-haptic texture augmentation on any surface using wearable vibrotactile haptic and an AR headset. This allows the user to freely see the augmented texture and touch them with the finger as if they were real. And this system is the basis for all the following contributions. And we now turn on the perception of such visual-haptic texture augmentation with the next two contributions. With this second contribution, we propose to investigate the perception of vibrotactile-only texture augmentation in AR versus VR. And this contribution, together with the previous one, was presented at the VR-ST conference in 2024. Texture augmentation of real surface has often been studied without visual feedback. Still, we know that the same haptic feedback can be perceived differently depending on the visual feedback. For example, the same haptic force feedback can be perceived differently in AR versus VR. A delay on the visual feedback can also affect the haptic force perception, but it has not yet been evaluated with wearable haptics. And a last important difference between VR and AR is that in VR, the hand is not visible and it can be replaced instead with an avatar, whereas in AR, the real hand is touching the augmented object directly. Therefore, we evaluate the perception of visual-haptic texture augmentation or haptic-only texture augmentation when touching with a virtual hand versus a real hand in AR versus VR. We use the same system we just presented to provide a vibrotactile texture to augment a real surface. And we use the fixed spatial period of 2 millimeters and varied the amplitude to create different level of roughness from very smooth to very rough. And we ask our participants to compare this 6 texture to reference one that was medium rough. We also created an experimental environment that we carefully replicated virtually, resulting in 3 rendering conditions. The real rendering was the real environment without any additional visual augmentation. AR rendering was the same environment, but with a virtual hand overlay superimposed on the real hand. And the VR rendering was the replica, the virtual replica of the real environment with the same virtual hand as an avatar. And note that the augmented surface was smooth and white, and the vibrotactile texture were only touch and not seen. So we conducted a psychophysical within subject user study where the participant tested the 6 vibrotactile texture against the reference in the 3 rendering condition. And here are the results of the study. First, we found that on average, the perception, the vibrotactile texture were perceived as smoother when touched in AR, rougher when touched in the real rendering, and VR was in between. Participants were also more sensitive to change in the real rendering, less sensitive in the AR, and VR was in between. It is as if the same vibrotactile texture augmentation was perceived as smoother when touched with the virtual hand. Participants also explore the texture faster on average in the real rendering and than compared to the AR and VR rendering. This suggests that participants had less confidence when exploring the vibrotactile texture augmentation when touching with a virtual hand. Participants also rated that both the vibrotactile texture and the virtual hand were very well synchronized with their real hand movement, and that the texture had very little delay compared to their movement. However, they found that the hand had some delays, a higher delay in AR compared to VR. And this is interesting because this delay was exactly the same in the 2 conditions, but it was perceived higher in AR. Therefore, we think that the difference in texture perception we just described is less due to the visual aspect of the virtual hand or the virtual environment, but more due to this perceived delay between the real hand movement, the proprioceptive feedback, and the virtual feedback of the virtual hand. To conclude this second contribution, we evaluated the roughness perception of vibrotactile texture augmentation in AR versus VR with a user study, and we found an effect as if the same vibrotactile texture augmentation felt smoother when touched with a virtual hand or rougher when touched with a real hand. And we think this effect is due to the perceived delay between the real hand movement and the visual feedback of the virtual hand, which was perceived differently in AR versus VR. This provides evidence the importance of minimizing visual-haptic, the delay of visual-haptic feedback, but more importantly, to ensure that these visual and haptic delays are perceived as synchronized by the user. Now, in this study, we didn't visually augment the surface, but with real objects, we often see the texture before touching them. That's why in this third contribution, we propose to investigate the perception of simultaneous and co-localized visual-haptic texture augmentation. And this contribution was published and presented at the EuroOptics conference in 2024. Texture of real object can be perceived only by vision and only by touch. And both senses are equally good and provide similar roughness sensation. And when the same object properties, such as texture, is perceived simultaneously by multiple sensory modalities, the different sensations are combined into the brain to form one single perception. Now with photography, we can capture the visual texture of a surface. And similarly, methods have been developed to capture and model the vibration generated when sliding over a surface. And it is then possible to reproduce this vibration using a vibrotactile device. And this method have led to the creation of VisuOptic texture database. However, such texture capture have not yet been used to augment real surface in AR. Our goal here is to understand how coherent VisuOptic augmentation of texture are together and how much each sensory modality contributes to the overall roughness perception. We employed the same system as before to render the visual and vibrotactile texture, and we used 9 textures with various levels of roughness from the Panoptic Texture Toolkit database. Participants performed 2 tasks. In the matching task, they had to find the haptic texture that best match a given visual texture. We separated and shuffled the 9 VisuOptic textures, and on each trial, the 9 haptic textures were displayed all at once, but 1 visual texture was displayed on all the surface. And participants had to explore each surface and choose the one with the most coherent VisuOptic texture. And in the ranking task, participants were asked to rank the texture according to their perceived roughness. They first ranked all the haptic texture without visual augmentation, then all the visual texture without haptic augmentation, and finally, as we can see on the video, they ranked the original VisuOptic texture pairs. Here are the results of the matching task. Participants were not able to match the original VisuOptic texture pairs. And in fact, they identified and matched clusters of texture with similar perceived roughness. Meaning that for one visual texture, participants hesitated between several vibrotactile textures. And note that the task was quite difficult because they had no prior knowledge of the texture, but also because they were missing additional visual cues such as the shape of an object. Regarding the results of the ranking task, we can see here the average ranking for the perceived roughness of the vibrotactile texture. More rough is here and more smooth is here. And we can see there is a strong consensus between participants as shown by the small confidence interval around the average ranking. This indicates that participants perceived very similarly the vibrotactile texture augmentation. There was also a good consensus on the ranking of the visual texture, but less than the haptic one, indicating that it was more difficult for participants to estimate the roughness of the visual texture. Finally, there was also a good consensus in the VisuOptic texture augmentation. We can see that the overall VisuOptic in green is always in between the haptic and visual ranking, but the VisuOptic ranking is always closer to the haptic ranking, showing that the haptic sensation had more influence and dominated the overall roughness perception. To conclude this third contribution, we investigate the perception of simultaneous and colocalized VisuOptic texture augmentation of real surface with a user study. Participants integrated the roughness sensation from both visual and haptic modality well. but haptic was dominating the perception. They also consistently identified and matched clusters of visual and haptic texture with similar perceived roughness. This study suggests that a set of visual texture augmentation can be combined in a current manner with a smaller set of vibrotactile texture augmentation. And this is important because capturing and modeling vibrotactile texture is a time-consuming and complex process. And there are very few databases of haptic texture available. Now, perceiving object properties such as the texture is an important interaction we have with objects, as well it is to grasp and manipulate them. Which we discuss in this second axis of research, where we improve hand interaction with virtual objects. And with this first contribution, we first propose to visually augment the hand as feedback for interacting with virtual objects. Visual feedback of the virtual hand is a key element for interaction in VR, but it has not yet been evaluated with AR headsets. In addition, AR headsets have rendering issues that makes depth perception of virtual objects difficult, such as a lack of mutual occlusion between the real hand and the virtual object, as we can see on the video, meaning that the virtual objects are always rendered on top of the real hand, because the AR display is closer to the eyes than the real hand. And this is important because manipulating virtual objects with the hand requires precise finger movement and placement in regard to the virtual content. For example, to interact with virtual button, windows, or slider, as we can see on the video. Therefore, a visual hand augmentation can help solve this issue by providing a feedback on the hand tracking, but also a feedback of the contact with the virtual object. To this end, we employed the same system as before, but we use the integrated hand tracking of the AR set to reconstruct a fully articulated virtual hand. We then select in the literature the most common visual rendering of the virtual hand used in AR. As a reference, we considered no visual hand augmentation. We then used the virtual hand to create mutual occlusion with the virtual object, meaning the real hand can mask the virtual cube. The tips rendering showed small rings around the fingertips. The contour rendering was a thin outline of the virtual hand. The skeleton rendering showed the joints and phalange of the fingers. And finally, the mesh rendering was a fully semi-transparent hand model. An important aspect of this augmentation is that they are constrained to the surface of the virtual cube, while of course the real hand can be inside the virtual cube. Participants performed two tasks where they had to place a virtual cube inside a target volume, a virtual target volume. In the push task, they had to push and slide along a real surface the virtual cube into the target, while in the grasp task, they had to grasp and lift the object on a volume above the surface. We chose these two common tasks because they are building blocks for more complex interactions, such as stacking objects or assembly. And we conducted a within-subject user study where each task was performed with all the visual hands and multiple targets. Here are the results of the push task. The skeleton feedback led to, on average, the fastest completion time, but also fewest contact with the virtual cube, meaning that participants were more efficient with this feedback and more confident in their interaction with the virtual cube. Regarding the grasp task, we didn't find any difference between the visual hand in terms of task completion time. However, more failed grasp and cube drops were observed with the non-occlusion feedback compared to the tips and mesh rendering. meaning that it was more difficult for participants to grab the cube and maintain it with having no visual hand augmentation or having the occlusion hand augmentation. In addition, participants showed an average grip aperture very close to the size of the cube with all the rendering, except when having no visual hand feedback, where they applied stronger grip, showing less confidence. Finally, participant opinion of the visual hand augmentation were mixed on many questions, except for the occlusion feedback, which was judged more difficult and less effective to use than the other visual hand augmentation. Participants also found that the interaction was more precise with the skeleton and mesh feedback than with the non-occlusion feedback, which is consistent with the performance results. To conclude this fourth contribution, we investigated the effect of visual hand augmentation on the manipulation of virtual objects in AR with a user study. Having a visual hand augmentation improves the performance, perceived effectiveness, and confidence of user compared to no augmentation. And the skeleton rendering seemed to be the best compromise and the most effective, probably because it provided a good detailed view of the hand tracking without hiding the real hand. Now, in addition to a visual hand augmentation, user can also benefit from wearable haptic feedback to manipulate virtual objects, which we investigate in this fifth and last contribution, where we explore the impact of the placement of the wearable haptic feedback on the hand when manipulating virtual objects and in combination with visual hand augmentation. And this contribution, together with the previous one, was published as a journal paper in Transaction on Haptics. Providing wearable haptic feedback for hand interaction in AR is challenging because the haptic device can affect the tracking of the hand, but also because the wearable haptic device should not impair the hand movement or the interaction with the real objects. The strategy consists to avoid to cover the fingertips or the palm by moving away the point of application of the haptic feedback to another position on the hand, such as the nails, the phalanx, the wrists, or even the opposite hand. A few studies have shown that such wearable relocated haptic feedback is effective for user to manipulate virtual objects. And it can be even more beneficial for user than having a visual feedback only of the virtual hand. However, these studies were conducted using an AR setup with a fixed screen and not with an AR headset. Finally, the different relocating positioning have not been compared with each other, nor they have been compared with the visual haptic feedback of the hand. That's why we propose to investigate this aspect with a user study. We considered vibrotactile feedback as it is used in almost all wearable haptic devices, and because vibrotactile motors are small and lightweight. We use two motors, one for the index and one for the thumb, to provide independent vibrotactile feedback whenever the fingertip touches the virtual cube. We then selected from the literature common positioning for wearable haptic. With the fingertip positioning, the haptic feedback was provided to the nails. With proximal, it was on the top of the proximal phalanges. With the wrist, it was on the side of the wrist. And with opposite, it was on the fingertip nails of the contralateral hand. And finally, the nowhere condition was the reference with no vibrotactile feedback. We also used two vibration techniques for rendering the virtual contact. The impact technique was a short vibration when the fingertip contacted the virtual cube with an amplitude proportional to the fingertip speed. This approximates the sensation of tapping the surface. The distance technique was a continuous vibration whenever the fingertip was inside the virtual cube, with an amplitude proportional to the distance of the virtual cube. And this approximates the sensation of pressing the virtual cube. We then conducted a within subject user study with a setup and task similar as to the previous contribution. As we are interested in visual-haptic feedback of the hand, we also included the skeleton visual hand augmentation, as it led to the best performance and perceived effectiveness in the previous user study. Here are the results of the push task. The fingertip positioning led to, on average, slower completion time compared to the proximal and opposite fingertip, and more contact with the virtual cube, which is surprising. And we think that the vibrotactile motors, when placed on the fingertip, could have disturbed the visualization of the virtual cube. And we think also that the opposite positioning, because of its unfamiliarity, may have caused participants to take more time considering the haptic feedback and making them more focused on the task and more performant in the long run. And we didn't find a clear performance difference between the visual hand nor the rendering techniques. Regarding the grasp task, the fingertip positioning and proximal positioning led to more failed grasp and cube drops compared to the opposite positioning, resulting in slower completion time. This correlates with higher average grip aperture for the fingertip and proximal positioning. And we think that the proximity of the vibrotactile feedback from the fingertip with the proximal fingertip positioning gave participants a better experience of the task, leading them to adjust their grip on the virtual cube in a more realistic way, so closer to the surface of the virtual cube, resulting in more failed grasp. And note that in the absence of vibrotactile feedback, participants applied on average stronger grip, showing again less confidence. And we didn't find either a difference between the visual hand nor the rendering technique in terms of performance. Overall, many participants appreciated the vibrotactile feedback, commenting that they made the task more realistic and easier. In particular, participants found the fingertip and proximal positioning the most useful for completing the two tasks. Similarly, the closer the vibrotactile feedback was to the fingertip, the better it was appreciated by participants. And as in the previous contribution, participants found that having the skeleton visual hand augmentation was more effective than having no augmentation, no visual hand augmentation. They reported that it provided a good feedback on the hand tracking, yet it was also felt as somewhat redundant with the vibrotactile feedback, which was judged to provide more accurate information of the contact with virtual cube. Finally, the impact technique seemed to be sufficient to provide contact information with the virtual object, as reported by participants. To conclude this last contribution, we investigated relocated vibrotactile feedback on the hand and its impact on the manipulation of virtual objects in combination with visual hand augmentation. We found that the delocalized vibrotactile feedback improved perceived effectiveness and confidence of user, even though they had lower performance with this positioning. That's why a vibrotactile ring worn on the middle or the proximal phalange is to prefer if a trade-off between performance and user experience is acceptable. And the visual hand augmentation was found to complement well the vibrotactile feedback, but we suggest to disable it at the moment of the contact or at the moment of the grasping of the cube to avoid redundancy with the haptic feedback. And to conclude this thesis presentation, We presented 5 contributions. Our objective was to improve hand interaction in AR using wearable haptics. We focused on 2 research axes. For the first axis, we investigated the perception of visuo-haptic textual augmentation. For the second axis, we investigated visuo-haptic augmentation of the hand to improve interaction manipulation of virtual objects. For the first axis, we first proposed a system for rendering visuo-haptic textual augmentation using wearable vibrotactile feedback and an AR headset that allows a user to freely see the augmented texture and touch them with a finger as if they were real, and it formed the basis for all the following contributions. Then, in a psychophysical user study, we evaluated the perception of such vibrotactile texture augmentation when touched in AR versus VR. And we found an effect as if the same vibrotactile texture augmentation felt smoother when touched with a virtual hand or rougher when touched with the real hand. And we think this effect is due to the perceived delay between the real hand movement and the visual feedback of the virtual hand, which can be different in AR versus VR. Finally, we investigated the perception of simultaneous and colocalized visuo-haptic texture augmentation. Participants integrated the visual and haptic sensation well in one perception, with haptic dominating the perception. And our results also provide evidence that visual texture augmentation can be supported by a smaller set of vibrotactile texture augmentation. Regarding the second axis, we first proposed to visually augment the real hand as feedback for manipulating virtual objects. In a user study, we found that such visual hand augmentation improved user performance, perceived effectiveness and confidence compared to no augmentation, with skeleton rendering of the phalange seeming to be the most effective because it provided a good detailed view of the hand without hiding it. Lastly, in a user study, we investigated moving the point of application of the wearable vibrotactile feedback to different positioning on the real hand. And we found that such relocated vibrotactile feedback improved user perceived effectiveness and confidence when it was provided close to the point of, close to the fingertips, even though they had lower performance with this positioning. And the vibrotactile feedback was also judged as more accurate than having a visual hand augmentation, which was still felt useful to provide a continuous feedback on the hand tracking. This work opens several perspectives as future work. Regarding the visuo-haptic augmentation, the realism of the vibrotactile texture could be improved by using not only the finger speed, but also the force, the direction, or the posture of the contact. Similarly, the quality of the visual texture augmentation could be improved and could have an impact on the overall perception of visuo-haptic texture augmentation. We also employed a texture model captured from a rigid probe, but this perception of texture with a rigid probe is different from texture perception from a finger. And capture and model of texture from the finger have been released recently and should be used instead. In addition, as we did for texture, other type or the object properties should be considered for visuo-haptic augmentation. However, it will be a challenge to augment some of these properties with wearable haptics, in particular on real objects that already generate strong haptic sensation when touched. That's why a visual augmentation of the object or of the hand could play a key role in expanding the possibilities of visuo-haptic texture augmentation. And attention should be given to the perceptual difference that are possible between different visuo-haptic augmentation of the same object property. Regarding the hand manipulation of virtual objects, the delocalized vibrotactile feedback was found useful for manipulating a virtual object. but more diverse visual-haptic stimuli may be required for more complex interaction or to manipulate different types of objects, such as deformable objects. Yet, this would require more complex haptic sensation and devices, and a compromise should be found between well-rounded haptic feedback, the wearability of the system, and the constraint of the AR system. Finally, in both axes, for both axes, participants in our study had varied sensitivities to the haptic feedback and different appreciation of the visual-haptic feedback. And it's important to investigate how to adapt the haptic feedback to the individual preferences and sensitivities, but also to the task and the context of use. However, the design space of visual-haptic feedback can be large and complex to understand for user. Therefore, this would require the development and the validation of method to allow user to easily calibrate and adjust the visual-haptic feedback to its preference and sensitivities. Thank you very much.
Thank you very much, Erwan. It was a nice presentation.
Thank you.
I will now let your reporters discuss directly with you. We will start with Professor Grubert. Professor Grubert, please, your turn. Take as much as you want.
Yeah. Erwan, thank you for the presentation. Particularly important, challenging, and I think also often overlooked topic, variable haptics and augmented reality. So I applaud you for tackling this. You showcased that you are able to conduct valid and independent research in this domain by looking at these two classes of problems, or you call them research axes, coherent visual haptic augmentations of surfaces, and then effective manipulation of virtual objects using in an augmented environment using augmented hands. So what I will do now, I will basically go from front to back through parts of your presentation and also through your thesis, and then ask some specific questions. Okay. So I think in your system contribution part, I think in your thesis it was chapter 3, and it was the first part of your presentation. You used a very particular setup. Okay, so you used, I'm not sure where this actually was, the box with a webcam and the HoloLens. I think this one, that's a good indication here. Yeah, so you have this technical setup. You have this external camera running at 60 Hertz, tracking these markers, fingertip marker and surface. And you also have this external HoloLens 2 device. So my first question is just for clarification. It's really because I didn't find details on that in the thesis. So how exactly did you calibrate the HoloLens 2 coordinate system with respect to the webcam camera coordinate system? So this is just a clarification question. So can you elaborate on that a bit?
Yes, thank you for your question. Yes, the HoloLens 2 is capable of self-localizing itself on the environment, and I used a very simple calibration step with the gaze pointer. I pointed with the HoloLens to the center of the 3 markers here, and using the different coordinate system, I simply did a rigid transformation between the two, and then manually adjusted to the millimeter. So it's a bit cumbersome to do, and I know from your work we can do a better calibration setup, but it was sufficient and effective for our experiment.
So, and you did that before every participant?
Yes.
Or so you turned on the HoloLens, had the SLAM system being initialized, so you didn't do any marker tracking with the HoloLens, but you used basically the SLAM system, and then
exactly.
You intersected array with the plane?
Yes, exactly.
Okay. So can you speculate a little bit about let's say the registration errors that there occurred, and what are, let's say, the different sources of this potential registration error. So I think on some further slides, you at some point show the augmented hands. At some point, I think it was in some of your user study slides. Yeah, for example, this one. Okay, so let's take the center. Yeah, and you already see from the pictures that there is a visible offset between the augmented hand and the physical hand, and this in itself can have various reasons, not just the registration error. It could be the hand model and so on and so forth. But can you speculate a little bit about the overall registration error that occurred in the system? So either you can or you cannot, and what are the potential sources of this registration error?
Yes, actually, everything was written on the thesis, if you want the reference, in the last section of the chapter 3.
You can also just tell me, so I don't need to read it.
If you are static, here the registration error is very low. Of course, it is noticeable. It's a few millimeters. And when you move, there is a constant latency delay in terms of time, meaning that the faster you move, the higher the spatial registration error is. And regarding the haptic and visual loop, they have different hand-to-head latencies, which are I don't remember the number, but I have noted there. Well, it's okay. And but because of the tracking here, we applied filtering to the movement and of the virtual hand. And so you had like 1.5 seconds delay between the real hand movement and the virtual hand movement, which is quite a lot, but it's a complex system and we have a lot of steps. So all the latencies of every step stack up very quickly. And I'm not really sure it could be easy to reduce these latencies. We could have used, yes, the headset to directly track the markers. However, the cameras are on the top of the headset, and if you do that, the hand is often outside the vision. So if we have used the camera of the headset, the finger movement will be lost many times. And having the external camera ensured very stable tracking. And I think the delays, the latencies on the visual side are quite expected for an AR system like that.
I would partially disagree, but you say that we had around 1.5 seconds of delay, and it's hard. It's a complex system. I see that to minimize that delay. But can you still try to think of ways that could still minimize that further? Because I think it impacted. That's my judgment now. I think it impacted your results. That was also evident. Yes, because you had this perceived delay in the augmented reality condition. So let's say if I would give you, I don't know, 500,000. I give you 500,000 euros, and 2 years from now, how would you minimize that delay?
I have maybe 2 different strategies. One is to integrate everything in the AR headset because combine everything in the hardware side. Have a dedicated chip to do all the tracking and feedback of the visual hand. And the other strategy is not to use an optical see-through headset, but to use a visual see-through headset, so that all the visual delay we have on the display is kind of cancelled, because it is now the reference of the real-world perception. And I'm pretty sure that with video see-through headsets, we could have a very low perceived latencies, as we can already try with MetaQuest 3, for example.
Yeah, I agree, and you're in a good company. All the big companies gave up on optical see-through headsets for now and going down the route of integrating it using video see-through technologies. I personally don't appreciate it, but it's a hard problem. I can see that. Okay, and also on that notion, so you have your marker on the top of the
Yes.
finger, right?
Yes.
And as far as I understood your system, the vibration start is, yeah, is that correct? So you
Yes.
touch the surface and you move your finger,
Yes.
and then you get some vibration. Okay. Then, like, how accurate was touching the surface? I mean, you obviously you have different finger heights. You have that marker here. When do you know when a person actually touches the surface?
There is also a calibration step before the experiment that is done with every participant. I ask participant to place a vibrotactile device, then to place the finger on the middle of the texture, and knowing that they are on this point, but the tracking point is here, do again a rigid transformation between the two coordinate systems. And I asked participants to keep the same posture during the experiment, and they actually did, because participants did this type of gesture during all the experiments. It was sufficient for experiments, but yes, how can I say? Yes, we use the finger position to determine if we are outside or inside the texture. And why? Do you want more details, or
Do you want to provide more details?
Yes, I'm pretty sure if we want to have more complex interaction, it could be hard to rely on such calibration.
Yeah, but I mean, it's sufficient for the setup.
It was
right?
sufficient for the setup.
Specific setup, and
yes,
where you design this.
But yes, of course, it will be a problem with more complex interaction.
And you did not find that this would create any problems with participants, whatever, having the vibrotactile feedback going off too soon or too late or something like that.
It would have been, but we did a lot of prototype and testing with colleagues, and it seems to be robust enough for our needs. And, yes, during our testing, one participant did that, touching. He did tack, tack, tack on the texture, and here it could have been a bit on delay. But as I mentioned, the haptic loop was quite fast, and almost no one noticed that the vibrotactile feedback was late compared to the real hand movements.
All right. I think in chapter 5,
yes,
your results indicated that it was at least partially difficult for participants to match textures effectively. I'm not sure which slide you discussed these results here. It was in chapter 5. Can you summarize again why you think that was partially difficult to match those textures?
I think it was difficult because the visual quality of the texture was not optimal. It was only a color display, whereas in the real world setup, we can see the light bouncing on the surface, and this aspect was missing. I tried to use normal maps to simulate such light bouncing, but it's not working with the HoloLens too. That's the first thing. The second one is that participants were displayed only with patch of texture, and it could be quite difficult to determine what type of texture it is. when you are in a real world condition, you often see the shape of the object or a context. So I think that is why the visual texture were quite difficult to determine what it is. And regarding the vibro-tactile texture, I think the sensitivities of the participants was quite different depending on the individuals, and so it created a lot of variation on the results. That's why I think it's really important to have a calibration step here, so that at the design time you want to provide some perception, some feedback to a user, but because of the sensitivities and preference of the user, we should adjust that to make sure what you want the user feel is aligned well with their sensitivities.
So at least I hear that part of the problem was the, let's say, the limited visual fidelity of,
Yes.
of these textures. Like, how would you maybe design a system or a study around studying the impact of visual fidelity on textual perception? Do you think what would be a relevant setup? What would be an independent variable and these levels of these variables, and how would you technically go about implementing it, either with a HoloLens or video see-through system or any other system?
Yes, I think we'll use a video see-through system because we have a complete we have a complete freedom on what we can achieve in terms of the visual quality now, and we could test different type of fidelity of the visual texture. We could have only patch of texture like this. We could add normal maps. We could have more high graphic texture rendering. And finally, we could try to have in-context texture and texture on objects. And we could see how much this different type of fidelity affects the visual texture perception. Yet I'm pretty sure that having only the visual texture is not enough. And if it's difficult for a user to understand the visual texture, touching it, as we can do with real everyday object, can help disambiguate and determine which type of texture I'm touching. For example, I can think that this is wood, but touching it, I can determine that this is plastic instead. So I'm pretty sure that having haptic feedback with virtual objects is quite important, even for texture.
Right. Thank you. I would have more questions in this part, but I'm looking a little bit on the time, so I'm going on to the next one. I think in chapter 6, I think it might be slide 49 or around it. I don't remember quite honestly. You stated and you found that this occlusion rendering technique led to more failed grasp attempts. I think that's the figure on the left, right? And also less user satisfaction.
Yes.
Can you elaborate a little bit more why you think this was the case with that rendering technique?
In fact, no users except one understood this was an occlusion feedback, and almost all participants thought it was a shadow on the virtual cube. And again, this is because of the visual delay of the virtual hand. And if you want to achieve such occlusion feedback, you need to have a very, very little delay between the real hand movement and the visual feedback of the virtual hand. Again, also, we are using an optical see-through headset, so merging the virtual and real world is quite difficult. And I don't think we can say that this is really an occlusion feedback, because yes, the cube here is a bit masked, but it's still displayed closer to the user and is not really merged in terms of depth perception to the real hand. So I think this kind of feedback, occlusion feedback, could be really effective in a video see-through headset, but with an optical see-through headset, I don't think it could be achieved with satisfactory results now.
So you talked about delay. I think registration error again might come into here. Did you also quantify the delay in this condition? Because now you don't have the external camera, you don't have such a complicated setup.
Yes, we quantified, and I don't remember, but I think it was 1 second of delay, maybe.
Perhaps it's quite a bit, right?
It was on the same range than we did with the external camera.
Okay. And maybe now my last question, I think, can you go to slide 65? Say your future work slide. So you mentioned how basically your findings in your research access could also be carried on. It's very good. And I think you mentioned the issue or the challenge of user-specific calibration.
Yes.
At the very end, can you also elaborate a little bit more about how maybe you would design a study or how you would develop an idea for the follow-up study in this domain?
I think we should know first the range of sensitivities of user for a given haptic feedback. We can ask participants the smallest haptic feedback sensation they can have, and to determine themselves the highest they can handle for maybe a short period of time and a long period of time. And then with this range we have for every individual, we could already calibrate quite correctly the amplitude. Then, for example, if we want to calibrate the frequency of this, I'm assuming a vibro-tactile signal for now for simplicity. We could ask participants to compare a feedback against reference one, a real reference one, and we can ask them to adjust some parameters to achieve a sensation that is the closest to a real reference. But this could be an issue because, of course, virtual haptic feedback is, of course, different from the real one. So we should also quantify this different offset we will have with real and virtual feedback. But I think, yes, I think it's already a good step if we ask the minimum amplitude and the maximum amplitude, because in our study, the amplitude were fixed for everyone, and I think it was the main issue we should solve now for future studies.
All right. Erwan, thank you so much for
Thank you very much
Thank
for your comments.
Thank you, Professor Gubert. Now the turn is to Professor John from Korea. Please, the floor is yours.
Okay, so can you hear me?
Yes.
Yes.
Okay, good. So actually, I'm quite happy to have more like people actually are interested in this topic, haptic augmented reality, because actually it was my PhD topic, like already 15 years ago, and still I'm doing it. So I'm very happy to have more people actually coming into this field. So because I'm actually haptics guy, so my question will be almost my every my question is will be related to haptic part, I guess. And I don't know if my report about the thesis is already given to Erwan or not. But anyway, my question will be, I guess, mostly based on my report I already submitted. First of all, so maybe let me just start from chapter 1 from the thesis. So chapter 1, it was good. It was good. But one thing I really recommend to add is about like general issue in haptic augmented reality, because like in one thesis we cannot really cover everything, but you specifically actually focus on specific topic in haptic augmented reality. But would be nice if we can actually include, like in introduction chapter, include a kind of general introduction and general issue in haptic augmented reality. For example, there are a lot of different issues. For example, like real-time, real environment estimation, and also contact detection, and also how to really make you feel a mix of real and virtual force, or real and virtual vibrations. So all these issues maybe can be put into introduction, even if you don't really cover them. So that is just my comment for first chapter. And let's go to chapter 3. So I have 20 minutes, I guess, right? Okay, so chapter 3. My main question about chapter 3 is that, so it is really like good approach to give vibration to the body part where you cannot really, I say it's indirect feedback, so that you can actually make user feel both virtual vibration and real touch, the feedback from the real touch. So that is actually one of the most important requirements for haptic augmented reality. So like moving vibration to the other part would be really nice approach, but I couldn't really find how good it is. I mean, so for example, you can directly put vibrator on your fingertip so that we can actually sure that the vibration surely actually delivered to the finger. But if you put vibrator to the other part, then how can you perceptually sure that the vibration is surely really delivered as if you are actually touching something with your fingertip? So that part, that proof, is not there in anywhere in the thesis. So I was actually expecting this from chapter 4 or chapter 5, but I couldn't find it. So do you have any comments on this? For example, this is, I mean, if this hardware system is, if you consider this hardware system as a big contribution of your thesis, then this should be included somewhere in the thesis. So how do you think?
Thank you for your question. Regarding the vibration propagation, I think there are many studies that shows us this propagation whenever you apply vibration on the finger or the hand, propagates in everywhere on the hand, and the perception is not so different than having the vibration localized. I've read that already. And we asked actually this question to participants in the study in chapter 4, where we asked them to say if they felt the vibration more on the top of the finger, or if they had the feeling of touching the texture on the surface. And actually it was interesting because opinions were quite mixed, quite varied. Some people were telling that, yes, for sure, it is on the top of my finger. And some were telling that, oh, yes, maybe it is on the surface. I think this illusion was created because the vibrations are very well synchronized with the movement. And which was surprising also is that even in VR, participants were I assume that in VR, people will feel the illusion of touching really a surface, but it was not the case. But I think that it's not so an issue in the end, because what's important here is not really, in my opinion, the perception. If user can make sense of it, it's enough to achieve the task we want to achieve. For example, at the end of the chapter 4, we propose, we elaborate very quickly a use case of projecting visual-haptic texture on a wall to be able to touch them. And we could also imagine a video conference where we could share visual-haptic textural objects at a distance, because right now the video conference is not sharing haptic sensation between us. And if we can make sense of this sensation, I think for me it's enough, even if it's not realistic at all. And maybe to elaborate a bit on this idea, when we are watching a movie, we know for sure that sometimes it's not for real, but still we are perceptually and narratively immersed in the movie. And I think we can achieve the same effect with haptic feedback. It's not maybe perceptually immersive. We can tell it's not the reality, but still, if we can make sense of it during the task and we are focused, immersed on the task to solve the problem or challenge, I think it's enough if it's usable for users.
Okay, so but still many researchers they try to make it as real as possible. So there is some room for this, and also it really like depends on the application. Where I mean, for example, if haptic can be used as just delivering the information, then realism doesn't matter. But like at least realism of the signal itself, the accuracy of signal itself can actually have a small or large contribution to the immersion of some environment. So in some applications, I guess. So what I expected is that anyway, at least this could be actually what kind of level of realism or what kind of level of signal, like physical realism, can be achieved using this device. Could be included somewhere in the thesis. So
yes, I think it's yes, we should try with user study. Yes, you're right. I agree. Yes.
Okay, so also it's quite a similar line of question. Is that in chapter 5, as far as I know, the algorithms that you used for generating vibrotactile signals is basically based on, I call it's data-driven basically from Robertson. So all the data is measured probably from a rigid tool, so that they only capture the vibrations, capture vibration from the contact between the rigid tool and the rigid surface. And as far as I know, like this rigid tool mediated interaction texture is quite different from a bare hand texture, as probably you guys know.
Mm-hmm.
And like applying this rigid tool-based rendering algorithm into this bare hand interaction doesn't really sound really sophisticated for me. So do you have any comments on this, or do you have any, have you observed any like artifact?
Yes, I completely agree with you. It is well known that roughness perception from a tool and from the finger varied significantly from each other, and the texture we used are captured from a tool and not from a finger. And there is two reasons for that. First, at the time we ran this setup, we didn't find any capture of texture from finger, but there is now some, and it will be very interesting to compare this kind of finger capture against tool capture in such augmentation setup. And the other reason is that this database provides visual and haptic capture of texture, and we knew for sure that the visual and the haptic capture came from the same real surface. And for us, it was really a start here, but yes, it's a bit simple, and we could improve a lot both the visual quality and the haptic fidelity with such system. And we wanted with just simple and very well-known captures of texture, how people will perceive them if we augment a real surface, touch with the finger. We could also run this same setup, but ask people to touch with the tool and see how much it improves the roughness perception compared to the real surface that have been captured. And I think many investigations should be done again.
Okay, so I understand that there's actually nothing there. No algorithm and no hardware actually to really recreate the bare hand touch. But that's why I actually keep asking you how real it is. I mean, for example, we can just run vibrations to deliver the information, like roughness value as information, but it's completely different from the feeling, real feeling of roughness, right?
Yes.
So sometimes some applications really need this real feeling of roughness.
Yes.
So that's why, keep asking you about this realism.
Yes, of course. Something that is missing and important is the friction feeling of the reaction against the movement of the finger. And I'm not sure we can simulate that with wearable haptics regarding augmentation of a real surface. Yes, we could augment directly the surface, but one of the rationale of this thesis was to be able to provide visual-haptic augmentation without altering, without modifying surface. And this is interesting because it allows, it opens a perspective where you can, in the future, create visual-haptic augmentation everywhere on every surface. If we modify the surface or use complex system to create a very realistic sensation, it constrains the user to a fixed workspace. It could be interesting for example, for medical setup, but if you want to have an everyday usage, like for example, a video conference, or I think such less realistic setup could be very useful while being simple to use for everyday users.
Yeah, sure. Yeah, it really depends on the application, basically. And move to the next question. So, in chapter 5 and chapter 6 is actually about psychophysical experiment. So you want to find some actually effect of some parameters in this augmented reality setup on the perception of texture, I guess. And I feel like this chapter 5 and chapter 6 is not really best fit to the setup or the system that you made until chapter 4, because in system you made is actually quite good, but it's not really stable system where you can have 100% control of parameters. For example, the delay and latency cannot be controlled actually in the system. But in chapter 5 and chapter 6, you want to really see, actually, at least in the discussion, you want to really see the effect of this latency, and which means you want to really see the effect of uncontrolled parameters or factors using the system where you cannot really control that parameters. So that is a bit my concern about this chapter 5 and chapter 6. So, it really works well because anyway, you made some system, you want to really use this system for finding some new findings. So that means something, but still it's not really 100% perfect fit. That's what I feel. So do you have any comment on this?
Yes, I completely agree with you. And of course, our results on perception should be confined with for sure more control system as you described in your studies. Yes, I agree. Yet, I think that no, sorry, I completely agree with you, and we should redo and confine the results with very controlled and high fidelity system like we can have with grounded feedback, haptic feedback, and maybe a more high-end AR headsets.
Okay, anyway, it's not really that critical issue in the thesis, so it's just recommendations. And my last question is that, like, the ultimate haptic augmented reality, I mean, augmented reality, haptic, whatever, is that you could actually, in haptic augmented reality system, you could mix, like within a single modality, you could mix real, virtual haptic feedback. For example, for texture modality, you can actually, like in ideal haptic augmented reality system, you can actually mix real texture and virtual texture so that you can actually do something like amplification of real textures or whatever, actually not just completely overlaying, but some feedback can be generated based on the real thing, real signals. So that can be kind of very interesting and meaningful. That would be quite interesting, meaningful applications. But in most examples you showed in the thesis, it's more like adding virtual feedback, I guess. So different modalities, for example, a feeling of a wall, feeling of real wall is mixed with the virtual texture. So that is kind of haptic augmented reality. But in some case, what I told you is that the mix within single modality could be really interesting. But and with your system, I guess it could be really possible to apply some really simple example under these categories. So that would be very interesting. It's just a recommendation. Yes. So for example, you have a real texture, surface texture. On the real surface, you are actually feeling this real surface, and then you can actually add some virtual texture with your system, and you can maybe modify or amplify or whatever interesting things can be done.
Yes.
So that could be, I guess, some interesting point can give you.
Yes, I agree. And we could use the AR headset to scan the real texture to augment, because prior to apply the virtual texture augmentation, because as you mentioned, I think with wearable haptics, we can now only amplify the sensation. And so if we have a texture with already strong roughness sensation, we can only add more roughness. And subtracting roughness with only wearable haptics, I'm not sure it is possible now. I don't know how to do it. So yes, if we are able to scan the surface augment prior to the haptic augmentation, we can subtract from the virtual signal what we already measured on the in terms of roughness on the real texture. Yes.
So I mean, you can do in real time, because you can just put accelerometer on your fingertip, and then real-time feedback or cancellations can be done.
Yes, yes.
I mean, that's what I'm actually doing now in my lab, so we can work together.
Okay.
And like one last quick question is that when I remember when I was doing this very similar system, building very similar system, this contact detection was really like problem, as mentioned previously. I mean, this contact detection is very important because delay between, like synchrony between two different haptic feedback can be really easily detected by human. So for example, you are touching real surface and you already feel the feedback from the real surface. And then you add something, then this discrepancy in timing becomes actually noticeable. then the augmentation becomes really like strange. So the detection of actual contact between contact of your fingertip to the real surface should be really accurate. So that issue is another issue that you can actually look into.
Yes.
But anyway, you already answered, I guess, in previous session.
I think we can add an additional answer. On the setup, if you're using a tool, often the end effector of the tool is really narrow. So I'm pretty sure it's really easy to notice a delay in the haptic feedback. But in our setup, we are touching with the finger, and there is a well-known fat finger problem with the touchscreen. And here it's a bit the same. Because the finger is quite large compared to a tool, I think we have more, we can have, it's less of an issue to have a bit more of delay. And it could be interesting to measure the perceptual delays, the delays that can be perceived with a tool versus touching with the finger only.
Okay, thank you. That's it from me.
Thank you very much.
Thank you, Professor John. We have done with the manuscript reporters, and then there are like two members, external members left, and the first is Martin Haché from INRIA Bordeaux. Martin, your turn.
Thank you, Sinan. And so thank you very much for this nice talk. It was very well prepared, very clear, and very efficient. So I really appreciate your talk, and it's really in line with the document that I found very clear, also very rigorous. So of course, it's possible to always do additional things, but yes, I really appreciated your document. So I had questions that were already discussed, of course, as always. But maybe to continue the previous discussion about the idea of in AR when you can really blend real and virtual and maybe experience and have feedback with real surfaces and then virtual or augmented surfaces. I was wondering if there's a risk that feeling real, having real sensation, real feedback on real surfaces, is there a risk that it can break the illusion with the virtual one or not? Because I mean, if all the feedback is virtual, maybe your brain accept this, and if you come back to real sensation, real feedback, maybe it can break the augmentation. Do you have an idea about this?
Do you mean the real sensation during the experience can break the augmentation, or alternatively touching augmentation and real surface can break the augmentation?
I mean, if all the feedback is purely simulated, maybe your brain can trust it more. It's easier to trust what is happening rather than if you switch back to real concrete feedback with real surfaces. So my question, yes, is: do you think that the perception would be better if it is fake feedback all the time, or if we can blend with a real feedback in the middle without any problem?
It is actually a very good question, and I don't know at all. But yes, I think you're right. I'm pretty sure that if we switch from the augmented experience to purely real can break the immersion. As we can experience every day, maybe with your phone, when you're on phone, you're focused, and if you watch something else, your attention has shift, and it takes some time to go back to maybe the phone. And then, yes, I think some equivalent effect could happen if you go back and forth to virtual sensation, augmented sensation, and real sensation. And you should add maybe some transition effect to the user to make the brain accept that is switching from an augmented world to a purely real world.
Maybe things to explore.
Things to explore, yes.
And also, I was wondering. So I'm really not an haptic guy, but from what I tested, I think it's super user dependent. It really depends on the person. So do you think you can imagine a plug and play system that you directly interact with the surfaces and it works, or you will really need calibration for each person before using it? Or is there a global range where it works? And
I think it works without calibrating the haptic feedback, because it is what we did in our studies. Yet, I think it's enough. It's a quick demo just to try the setup. But if you want to have a longer use or a more personal use, or even a professional use, it's a good time to invest to calibrate a bit. And I'm pretty confident we can have very short and effective calibration in a few minutes for the user. And I think we can have a plug and play system, but only for short experience. And it would be better to take some time to calibrate for every user for more personalized use.
Okay, thank you. And also another question I had was about sound.
Yes.
So what were the conditions during the experiment? There were absolutely no sound when touching surfaces, or there were a sound and a controlled sound or not? And do you think that having the sound feedback can change the perception? I don't know. I don't know this subject, so if you can explain me a bit.
Yes, actually, sound feedback is a really important cue when we are touching real textures. And new methods have been developed to improve such visuo-haptic capture to also include sound sensation, so you can play back the tree sensation. In our case, the vibrotactile feedback created very small sounds. So we masked it using headset, sound headset to the user, where we played some white noise to prevent them to hear the vibrotactile feedback.
Okay, thank you. And yeah, then no, yes, yeah, you answered, so it's okay. And maybe maybe a last question, more general. So really about improving manipulation of virtual objects with haptic feedback. I think it's very clear why it is useful, and it can be very generic task. For augmenting textures, for me, it's less clear why we need it. So in some very specific cases, I can understand that, yes, it can be useful, but as a general rule, For me, it's not completely clear. Yes, why we need it. And for example, let's suppose that you create a startup, a company, and you want to convince people that it is very useful to have this as a new tool, and we need to invest money and time and material to do it. To you, what are the main application domains where we wouldn't need it? You mentioned, for example, video conferences with tactile feedback. I'm not completely convinced. Can you try to convince me a little bit more why we need it?
I think it could be nice to have some texture feedback, maybe for real estate or renovating a house. Maybe I would like to buy this house and change the wall to have the wall behind you. And so with such setup, I can project the same feeling, see and touch the feeling of having the same wall than you have. And yes, it could be nice when you want to renovate a house or buy it. But apart from that, yes, if you want to buy some materials, how can I say? It costs a lot of money to have a lot of materials for a manufacturer store, so they can have less materials and let the user try the materials by seeing and touching them and order the materials. But I think texture perception seems not useful because we are so used to touch things in everyday life that we don't notice how important it is. And when you manipulate virtual content, of course, you'll like often tactile feedback. And if you see the texture or if you visually modify a real object, and you're unable to touch texture, even if it's not really realistic, it breaks a bit the illusion because what you touch is not augmented and you can only see. So I think it's something that is quite important when we interact in everyday life, but we tend to forget it also. So yes, I think it's quite important to have a texture if we don't want to break the illusion of the virtual and augmented object when we touch them.
Sorry. Okay. So, thank you. And I think I am going to stop here and switch off my mic to avoid.
Thank you.
Thanks.
Thank you, Martin. Before giving the mic to your supervisor, I'll have a couple of comments and observations. So this is an examiner, not president. So first of all, congrats, because I think that this work is quite brave, because this is like horribly complicated. And especially like saying that, okay, I'm going to focus on augmented reality. So I see the using a real see-through headset. So I got like the real image with virtual things on top of it, and trying to make haptics on it, and trying to understand how people works, and using also wearables, so very limited haptic feedback. The wearable tactiles, it was a very interesting and brave endeavor. So I congratulate you for that.
Thank you.
And as an academician, I would like to thank you for starting to work on that, because definitely we are looking at something that's necessary and needed in the future, when maybe the rendering techniques will be better, when all that is latency issues and everything will be solved by technology, because I mean, there are things that you cannot have, you cannot do everything, right? And so I think that's a useful work, and that's like opening the way. That's quite interesting.
Thank you.
A couple of comments, like I had written lots of questions that's been all asked by previous examiner, so that's cool. I won't have to talk much. Maybe let's start with this speed latency, because the haptic rendering that you are using, it's very much based on the speed estimation.
Yes.
And the way that you have used this, do you have calculated this estimation? It's like forcibly introduces a little bit delay because you are doing it there. Would you like, maybe it would be interesting using another speed estimation techniques like Kalman filters, which have less delay? I think do you think is it worth it, and would it have like some positive effect on the rendering?
Yes, of course, the less delay you have, the better it is, and Kalman filter should be used, could be used instead. And maybe we could also use the accelerometers or internal measurement unit also to have maybe faster estimation of the finger speed.
Yeah, maybe that would maybe a little bit change the behavior. And also, yeah, that like it has also been pointed out, this latency and delays like affect very much the perception. So there is a word that you haven't used in this work and in the manuscript, and that's, I think it's interesting. It's like pseudo haptics.
Yes.
So can you comment a little bit on that? Because I mean, with all these delays and everything, I think we are a little bit in the middle of using pseudo haptic techniques with vibrotactile augmentation, and this is somehow all mixed up. So
yes. Yes, actually, it's a good question, and we could use the pseudo-haptic feedback to affect the haptic augmentation. And, it is something that is being done already by my supervisors, and I'm pretty sure we have plenty of combination to explore with pseudo-haptics. And maybe we can, this kind of effect we found, we can counter this effect with a pseudo-haptic effect, yes. So I think it's something to explore, definitely.
maybe in the next PhD.
Yes.
Okay, there's something else related to what I do. So, Doc, we are starting looking at similar problems, but we haven't gone on wearable haptics, but we have trying to look at this with graspable objects. So the idea is that using a single object that can stand in for different virtual objects depending on the situation, and trying to change the texture. So can you comment a little bit how this work on wearables can be translated on graspable haptics?
This is actually a very good question. And
you're making me blush.
I think, yes, actually, it's a very good question, because with rigid objects, it's okay to provide the contact, the feedback only on the moment of the contact, and you can constrain the visual feedback to the object. But when you are able to deform the object, what type of feedback and when to provide and how long, I think it's really something to explore. I'm pretty sure that wearable feedback with pressure could be maybe more interesting, because you can provide more or less pressure on the hand. And again, when you deform the object, the visual feedback is really strong. So having a compelling touch feedback maybe is really important to not to break the illusion, but maybe also it's less important because you have already very strong visual sensation. So maybe a simple haptic feedback is enough to support the visual effect of deforming the object. And it's really a tough question. I really don't know. And
I don't expect you like to solve the ongoing PhD work. I mean, it will be like interesting, but it will be nice anyway. Okay. So yeah, so maybe can you think it would be interesting to mix up this graspable objects and vibrotactile variable feedback? So maybe you can change the texture on touch or this kind of stuff, or is it a little bit overkill?
Yes. Ah là là.
Okay.
No, I think maybe it's could be useful. Like the tasks we used are really like typical virtual task where everything is simple shapes and simple colors. And maybe if we want to simulate a more realistic environment, maybe I would like to have a more complex object on my real table here, and seeing the texture, seeing a complex shape, and being able to have compelling haptic feedback when interacting with them could be very much important. But on the two tasks we presented, I think texture is not necessary, but if we want to correctly blend complex objects into the real world, I think we need compelling touch feedback. This includes texture.
Okay, thank you. Just a couple of questions that I forgot to ask earlier, little by curiosity. Can you get back the experiment with the 9 textures? The experiment
Yes.
with the 9 textures. I was wondering, how was the performances of the matching task with real textures? I guess, I mean...
Yes, it's a good question. And,
do people do well with real textures, this kind of thing, or matching is always difficult?
I think they will do better because previous studies have shown that the texture perception only by sight is as good as touch perception and provides similar results. And yes, I think it will be better, and it will be not perfect, but I think it will be okay with real textures. So this means that we have plenty room of improvement with such setup, in particular for the visual texture.
Okay. Well, thank you very much.
Thank you very much.
It's okay for me, so I don't think you'll have hard question afterwards, but you never know. So maybe we'll start with your thesis director, Eric Marchand.
Thanks, Ilan. So first, I'd like to thank all the jury members to be there. It's not always very easy to come here due to strong weather here in Rennes. So thank you for that and for the other being in video conferencing from Korea. The hour is perhaps not really perfect. When Maud and Claudio asked me to co-advise your PhD thesis, first I thought, since it was about also augmented reality, that it will be a computer vision part of AR, because that's my area. But actually, no. So it was quite uncomfortable for me, but actually at the end I learned a lot about haptics and about user study also, which is something I'm not used to. So it's always nice to learn some new scientific area, and I appreciate. There was some little bits on computer vision that we will speak about, but I was glad to use that a little.
Yes.
So you provide a significant amount of work and quite original subject. It's not always in the literature. It's quite new. It was not easy because the IR headset are, let's say, not so good. So perhaps it will help. I thought the computer vision part is finished, but finally, certainly not. No. There are still a lot of work to do with that. Anyway, you managed to do some nice contribution, I think, with three papers, and I'd like to thank you for that. Just a last sentence. I also like to thank the University of Rennes, which provide you with your fellowship, and it's always nice to acknowledge people who paid the salaries. Thank you.
As the same as for the trips to.
Yes. That's all. Thank you.
Let's move to Claudio. Claudio Pacavetti.
Thank you. So thank you very much for the presentation. Thank you very much to the community for being here and online. So it was really nice topic. So we started thinking about it in small modes. You know, we realized that it's going to be very interesting scientifically speaking, but also very hard technically speaking. So this is why when we talked with you, we saw that you had real interest for the topic. You already a bit of experience, so this is why I picked really the right person to is that really combines scientific interest but also technical expertise to carry out things. There are a lot of things, and we have seen. And I think we have answered many questions during your PhD. I'm not sure if you answered more questions. We open more questions at the end, so we might need another couple of PhD. You did a great job. I really liked your attention to detail, very precise, with the different topics. So you never wanted to submit until everything was perfect, which is something that sometimes took a bit more time than we expected. But I have to say that all the results were really great, and also this presentation, I think it's a proof of this. I also want to praise your interest for studying, everything from the statistical analysis. Most students simply want to have working knowledge of everything, to do things as fast as possible. Everyone really wanted to understand things, which is something I would say quite exceptional. And so I think you should really be proud of what you've done. I think the very good publications, presentations, and so today is the proof of all of these results. And I'm also very happy because I think it's a very good relationship throughout this year. So it was also a pleasure to get to know you also from that side. And,
Thank you, Claudio. And let's move to conclude to Professor Marshall. Maud, please.
Thank you, Mr. President. As Eric and Claudia, I would like to thank first all the committee members for being there online or in France today. So thanks a lot of big thanks to Jens and Soki for their reviews and for reading all the manuscripts and for their reviews. And thanks Jens for being there in person, even when you had a trip yesterday was not as expected. And thanks Soki to stay online, even if you have a time zone difference, it's quite quite big. And thanks to Martin and Sinan to having accepted to be there. I think Martin, you already knew Erwan before because Erwan was an engineer in Martin's team before doing his PhD, and so I hope it was great for you to see how Erwan managed to work on these topics these last 3 years. And thanks, Sinan, today for being there and for having accepted to be the president. So let's talk about you and now, Erwan. So as already mentioned, so at the beginning we have a white card for working on wearable haptics and augmented reality. And when you look at these two topics, which could be at their own topics, and then you have to mix them all together, and still it's a very wide topic with a lot of research directions. And when we start and we are doing some brainstorming at the beginning, and of course there were many research directions, and I guess you struggle a little bit with this wide number of possibilities that you could have, and the wide number of research directions that you could have. And we should note that Erwan is asking a lot of questions to himself, and so we have to he has to. I guess you understood that it was normal researcher life to ask you so many questions every day. And at the end, you managed to find like specific question we could answer on that. And for that, you did like, I should really highlight this, you did like a huge amount of technological contribution, because it's not easy. We have like technologies that are evolving a lot this last year, especially in AR and also in haptics. So in both, so we see that like even today, some of our experiments are no more up to date, like they are obsolete for some of them, because we have like new devices. And this is evolving a lot, which means that you have like to take into account all these technical contributions in what you did, and you highlight a little bit in your manuscript the setup, but it was like a huge part of your work, and it should highlight it here. And in addition, you were like very new to conducting and designing user studies, and you managed to carry out like all this work on user study. And of course, I mean, with this user study, like you have like so many parameters that we could discuss, and we already discussed during like the questions about these parameters, and of course, like there are like an infinite number of possibilities for doing other parameters. But at the end, you managed to put everything all together and to have a story of what we did and all what we thought about. And of course, we still have like so many perspectives on this work. But what I hope is like you are proud of what you have done with all your contribution. And I really would like to congratulate you for that. And I wish you all the best for the future. So congratulations for all what you have done these last 3 years.
Very much.
Thank you, Maud. Well, I think we are done for the first part. Again, congrats for your presentations. Next, we will be moving out, I guess. Yeah. Okay, and then we'll be back here.
Yeah, so
Thanks,
for
Stefan.
just for Seoki and Marta, so just like if you can connect to the Zoom link, and then we will move to the other room in 5 minutes. Thanks.
Quel suspense. Okay. How are we gonna do it? Sorry. It's coming. Okay. Sorry. Okay. I'll do it in English then. Erwan, so you made a very well structured presentation. The jury found that it was quite clear and nice to follow. We found that you have a good explanation of the context and your research topic, and you justified why you are you focused on this issue and how you're going to work on that. Your presentation showed that you get some clear contribution on this interesting and difficult topic, and we have seen that you have worked on the integration of this augmented reality system with a virtual vibrotactile devices, two different ones, and we agree that it was a difficult task, and there was lots of technical issues on the way. And despite that, you have made a quite interesting and good work, and you have designed using the device interesting user studies. You worked on the perception of the augmented surfaces as well of the manipulation of the virtual objects, and you had a difficult task of analyzing these results, which were like lots of different complicated parameters, not all easy to control. And in each cases, you have came up with a sensible discussion that put forward your contribution, and you were quite well aware of the technical limitation and how it will happen. And you had also good insight on that. And also during the questions and answer, we found that you answered like to the point, thoroughly, honestly, and it was quite easy to follow, and the resulting scientific discussion was quite good quality. And the jury has appreciated your contributions. And for all those reasons, we have decided to grant you with the title of Docteur de l'Université de Rennes en informatique. My congratulations. So, your turn. Again.
Est-ce que je veux savoir d'abord? Oui. Oui. Je vais le faire en français.
Oui, yes.
En présence de mes pairs, parvenus à l'issue de mon doctorat en informatique et ayant ainsi pratiqué dans ma quête du savoir l'exercice d'une recherche scientifique exigeante, cultivant la rigueur intellectuelle, la réflexivité éthique dans le respect des principes de l'intégrité scientifique, je m'engage, pour ce qui dépendra de moi, dans la suite de ma carrière professionnelle et quel que soit le secteur ou le domaine d'activité, à maintenir une conduite intègre dans mon rapport au savoir, mes méthodes et mes résultats. Je voudrais remercier aussi mes encadrants pour votre confiance, pour votre disponibilité et pour vos nombreux et précieux conseils qui m'ont apporté dans ces 3 années. I'm also very grateful to the members of the jury for agreeing to review my thesis, for your presence today, and for all the interesting and valuable feedback and comments. Et je remercie également tous mes collègues, le temps précieux que nous avons passé ensemble et les nombreuses et passionnantes discussions que nous avons eues et l'aide qu'ils m'ont pu m'apporter, particulièrement Lindsay, Antoine, Guillaume et Thomas. Et enfin, je remercie plus particulièrement ma famille, mes amis et Agathe pour m'avoir soutenu et accompagné durant ces 3 années de thèse, et surtout pour préparer le pot. Que je vous invite à aller déguster avec nous. Merci beaucoup.
Voilà.